Okay, I'm very honored to have Stephen Hawking attending this talk. And so I'm going to talk about the early work that I did on particle reduction, and also the most important thing with regard to particle reduction by the expanding universe that we might soon be observing. Planck and BICEP 2 are collaborating now on a project to try to determine whether or not we're getting gravitational waves coming from the earliest stages of the exponential expansion of the universe. So first thing I want to say, let me just see this thing works, so let me just see. Okay. Am I going the wrong way? No. Sorry. Okay, we're back where we were before. So we may soon see the B-mode polarization patterns in the microwave background that are produced by gravitational waves coming from the very earliest universe. Everybody knows that. Right now, we don't know it's true yet, because dust also produces similar patterns, but there are ways to differentiate them, and Planck and BICEP are collaborating on that as we speak, and should have some results hopefully in a year or two, and definite results. Okay, so I want to explain how the original, I thought you might be interested in the history of how a novice, so to speak, graduate student went about trying to show that this process of particle production by the early universe does truly occur and produce real particles. And I started my PhD thesis around 1962 at Harvard. I was very lucky that Sidney Coleman agreed to be my advisor on a project which was out of the mainstream, far out of the mainstream. And that was to look at general relativity and the expanding universe and try to ask the question of whether particles are created, and to prove it in such a way that it was utterly convincing. And so the idea was that the only thing we knew at that time was that in flat space-time, we knew how particles are described by quantized fields. And so we didn't really know, at least I certainly didn't, how to describe particles during the expansion of the universe, or really what quantum field theory looked like during the expansion of the universe, or should definitely look like, let's say, convincingly. So the idea was to start from Minkowski space, and then start, say, with a certain number of particles. We chose 0 to begin with, the vacuum state, and then to propagate into a expanding universe, Friedman, Robertson, Walker, expanding universe, and let it expand in whatever way, with certain derivatives continuous, and the function A of t, the expansion factor, continuous. And then after a time to very gradually go to a flat Minkowski space again, but of a different, scale, one with a much larger scale. So you had an expansion of the universe, and then a gradual start and a gradual stop. Start with no particles, and then see if there are particles left at the end, because again, you know what are particles, or how to describe them by quantum field theory. But during expansion, you don't really know, or did not know. And in fact, there's some very interesting points about that with regard to renormalization. And so let me just, oh boy, I see, I have to use this. Okay, so if you don't mind, I'm going to sit so I can see the screen and I don't have to look up at that thing. So Sidney Coleman agreed to be my advisor, and I started doing this thesis work. And I should use that. Thank you. Yeah. Okay, so I already explained the basic mechanism that we were using. And so we started with no particles present, and actually I notice I'm on the Bunch-Davies vacuum at this point. But so I'm just pointing out, I guess, sorry. Okay, so the various cases I considered, among others, were the radiation-dominated, matter-dominated universe, and also what was known then as the steady-state universe, where you... Okay, I thought you wanted me down here. Okay, so, and as we'll see, the results I got also allows you to immediately obtain the results for the exponentially expanding universe of de Sitter, which was then actually known as the steady-state universe. And in fact, when I was, after I got my PhD thesis, I was hired by Bryce DeWitt, or before I got it actually, and there was a seminar given at Chapel Hill by Fred Hoyle about the steady-state universe, and I'll discussion I had with him, in which he, of course, believed that the universe was always the same, the perfect cosmological principle, and that we had a de Sitter. This is the Bondi-Gold and Hoyle steady-state theory, and Hoyle was, I'm told, the last person to continue advocating that theory. We know that the universe was not always the same. But anyway, he gave a talk on that, and then I showed him that with my as yet unpublished thesis, the part I sent to Bryce DeWitt, in fact, I showed him that we could maintain a steady-state universe, but that the particle number creation rate would be much higher than what they wanted to have in the present universe. So we couldn't actually get the steady-state universe, but we could still maintain a exponentially expanding de Sitter universe, and we could figure out that there was a very high creation rate involved, but Hoyle was not interested in the result at the time. He was not happy with that result, and that I showed him, And, that was before the days of the inflationary universe, and I'll go into that. So we should be going down by a half a thing each time. Okay, so the first thing I considered was this gradual expansion from an initial flat space to a late flat space. And I considered the minimally coupled scalar field, massless and massive, and I found that there was particle creation. That is, at the late time vacuum, when the universe stopped expanding, there were particles present, even though in the Minkowski sense. And furthermore, I just dynamically propagated the field theory from the initial Minkowski space to the final Minkowski space. And in the meantime, that gave you everything that was going on. You didn't have to know what happened in the middle. So first thing was, I guess it's just interesting to explain this. Well, we got particles and present in the final state, and so let me just show you how we got that. And also, I think I should say something that's important is that I wanted to also now see what was going on during the expansion of the universe. And for that, what seemed to be going on was that you had an infinite number of particles present during the expansion. But if you went from non-expanding universe to another non-expanding universe, during the times when you're in Minkowski space, all those other particles that gave you infinity went away. And since I don't cover it all in here in detail, the thing I wanted to say was I had been studying measurement theory, quantum measurement theory, and I had actually looked at what would happen when you try to measure particle number, because I truly believe we live in an expanding universe, and that we better know how many particles there are in the expanding universe, not just when it's flat or something like that. And so I analyzed it from the point of view of measurement theory and renormalization in a rather novel way that is different. Anyway, it turned out that there are these virtual particles that appear during the expansion, and that was why we were getting divergences. But that when you go through the renormalization process, which when I started I was using in that case was this was before dimensional regularization, things like that. I was using something called Adiabatic Regularization, which I used up to second order, and later with Steve Fulling, and actually third order. And then with Steve Fulling, for the energy momentum tensor, you have divergences which require you to go up to fourth order. And we did that for the energy momentum tensor in 1974, I think it was. Okay, so, and as far as the gravitons are concerned, I looked at Penrose's and other conformal fields that Penrose had given for the spin 2 field and the other spin fields, and I showed that conformal invariance. He had looked at it classically. I showed that conformal invariance would give you would give you no particle production for any kind of expansion. as long as it didn't have discontinuities. So this was all done in the thesis. And this thing's not working well, so I'm going to instead go to here so I can actually see what I'm doing. Okay, so let me just show you quickly the, so I published this stuff in 1966 and all that, and well, in my PhD thesis in 1966, and then in Physical Review Letters in 1968, and several other articles based on the thesis. Now, an important point was that Einstein gravitons, as you know, obtained by linearizing the Einstein equation, those do not obey the conformally invariant wave equation, and so we believe there is particle reduction if the Einstein equations are the correct way to go. And as early as 1946, E.M. Lifshitz had looked at the Einstein equations, linearized Einstein equations, and had actually shown that it could be reduced in what's now known as the Lifshitz gauge. It can be reduced to the minimally coupled scalar field equation for two scalar fields, one representing each of the polarization states of the graviton. So it turned out that, by good fortune, I guess, but it was known to a lot of people, I suppose, but not to me at the time I did the work, that the scalar, minimally coupled scalar field equation was this Lifshitz equation for linearized gravity. And so the result I had obtained was good for gravitons. Later, Larry Ford and I, in fact, looked at this in detail. But a paper on this was published by Leonid Grishchuk in, well, I have it in the reference, but it was around 1975, and he used my method to, he knew about my work and used it to figure out what would be expected in the way of graviton production, the kind of thing we're now looking for experimentally, where you can actually expect to find these things. And it turned out that Larry Ford and I did a much more careful job in 1977 and published in Physical Review. And one of the things we showed in our paper was that there were spurious infrared divergences present in Grishchuk's result because of his, he didn't apply his boundary conditions properly. This was, again, something that had to do with I guess, when you have too fast a slowdown, you can get virtual particles at very low infrared energy. So Larry and I, Lawrence Ford is here, for example, and together we actually showed how to do it properly. And so okay, so that's in Physical Review, 1977, as I said. And so finally, in section 3, I'll talk about see, how, again, from the equations I'll show you in a minute, that are for general AFT, general expansion, you can already get the result immediately from that for the, in the case of the 10-dimensional dimensional vacuum state of de Sitter, which was, of course, known, and is the same vacuum state as comes about when you have during inflationary expansion. Okay, so let me jump to an equation to wake you up. All right. Oh, I should also mention so I'm going to go over the equations, which you probably all know by now. Anyway, oh, I just wanted to say in my original paper in 1968, I'll quote before I go on, the reason I knew, of course, that there'd be large particle production when the universe was small and was expanding rapidly. And that was already in my 1968 paper. And what I wrote in my conclusion was, to quote it here, the particle creation in the expanding universe at the present time is quite negligible. However, for the early stages of a Friedmann expansion, it may well be of great cosmological significance, especially since it seems inescapable if one accepts quantum field theory and general relativity. In considering the large amount of particle creation taking place in the early stages of an expansion, it is necessary, of course, to take into account the reaction of the matter created back on the gravitational field. Furthermore, it may be necessary to consider the effects of the quantization of the gravitational field. Therefore, no conclusive quantitative result can yet be reported here concerning the primeval creation. Okay, well, the conclusion of my paper emphasized the strong effects that particle creation would have on the early expansion of the universe, so the reaction back would have to be taken into account. The first such calculation was done by me and Stephen Fulling, who is here, sitting in the last row over there, and this was what we did was actually a numerical calculation, and we considered a Friedmann-Robertson-Walker universe, actually in this case a closed universe, which was collapsing, and we showed one could get a bounce, that there were very large fluctuations of between positive and negative pressures and stuff if you took the state appropriately. This was the kind of state that you have, for example, in superconductivity. And we took a simple example of that as our quote-unquote vacuum state. And by numerical evolution of the semi-classical Einstein equations, we showed that a bounce could occur as a result of the particle creation process, thus avoiding the cosmological singularity. Our result also demonstrated that the classical energy conditions can be avoided through the creation of particles by quantum field theory in an FLRW universe. Okay, so as far as let me just get to it when I get to it. And then I mentioned already about using methods of quantum measurement theory to develop the method of adiabatic regularization or renormalization as applied to the particle number operator during the expansion of the universe. And as I mentioned already, in 1974, Steve Fulling and I extended the adiabatic regularization method to renormalize the expectation value of the energy momentum tensor, and that required going to fourth order. Okay. And then, so an interesting sidelight is that I was hired as an instructor to teach at the University of North Carolina, one of the sponsors of this meeting, for 1966 and 1967. The reason was my thesis advisor was away in Europe, and I had to wait until he returned to Harvard in 1966 to fly to Boston for my thesis defense. And Bryce DeWitt hired me as an instructor in a position that had been held by Peter Higgs, in fact, at Chapel Hill. Okay, and I passed. My committee consisted of Sidney Coleman, Sheldon Glashow, and Walter Gilbert, who won, except for Sidney because he passed away too soon, who won Nobel Prizes, Glashow and Gilbert did, and for very different reasons. Gilbert was Schwinger's assistant, in fact, at Harvard, and eventually he got ideas about biology and showed how to sequence the genome in a way that won him the Nobel Prize in chemistry, actually. Okay, so, and while teaching, I already mentioned I went to this colloquium by Fred Hoyle, and I spoke to him and talked about the very rapid production of particles by an exponentially expanding universe, which one can immediately obtain from the results that I had in my thesis. Okay, but I did it for a general AFT. Okay, so let me just start out here with the spatially flat Robertson-Walker universe with scale factor AFT and the minimally coupled scalar field equation. Here I'm taking, including a mass m squared, but it need not be 0. And box is the covariant Laplacian operator, 4-dimensional Laplacian. Okay, so so if you just take and you use the symmetries of your space in the Friedman-Robertson-Walker spatially flat one, this is the equation you get, and there's a time derivative here, and A is a function of time. It's the expansion factor. You just expand your field. I'll go through this quickly because everybody knows this already. And so you expand your field in terms of basically creation, annihilation and creation operators and wave functions. And so in this case, we have spatially flat universe, so you have e to the ik dot x as your spatial part, and then hk of t is the time-dependent part. And it satisfies, when you work it out, it satisfies this equation involving a dot over a and a double dot over a, where a is the scale factor of the universe, and hk, remember, appeared in the wave functions that are inside the quantized field. Okay, so, and you can solve it for various AFT, but we can work generally also. Let me skip this because we don't need to use it to get the answer. Okay. All right, so I already explained that I worked in a situation where you go from spatially flat to more or less arbitrary expansion, though it has continuous first and second derivatives, at least. And then you go back to spatially flat, and you can determine without going through measurement theory how many particles are present at the end and at the beginning. Okay, and so I started the universe expanding very slowly, so that you knew particle number turns out to be an adiabatic invariant, as we would expect. Okay, just like the number of quanta in a simple harmonic oscillator, basically, if you compare equations. If you change the frequency slowly, your solution turns out to be the Liouville approximation for the harmonic oscillator with a slowly changing frequency. And when the universe starts from not expanding and then slowly starts expanding, we know what the wave functions or the time part of the wave function looks like. And this thing here, square root of k squared over a of t squared plus m squared over omega k of t is just the basically energy or the energy of your mode k. Okay. And it's good in the limit that all time derivatives of a of t smoothly approach zero. We did look at this very carefully and rigorously using results that were in the mathematical literature, and which I don't have time to go into. So you have a general, now we go through the expansion, we come back to the end, and when you're in the final Minkowski space, after you've expanded in some fairly arbitrary way, you're going to have coefficients alpha k and beta k times these things that look like WKB solutions. They're the Liouville solutions for a harmonic oscillator with a slowly changing frequency. And alpha k and beta k are just complex constants which have to obey the equation alpha squared, absolute alpha squared minus absolute beta k squared equals 1. And that's a result of the conserved Wronskian of the differential equation satisfied by h of k of t. So, so here I'm taking a of t perfectly continuous, a C2 function, that is with continuous and continuous first and second derivatives at least. Okay, so okay, and let me skip this since it's just a. Okay, and now in your late time Minkowski space, now you've let the universe expand in some arbitrary way. Now you go to a late time Minkowski space, a of t going to a constant again, very slowly and continuously. And you now have, or because of what I wrote, we can write our field, very same field phi, in the late times. You just put things together and you see that you're, again, as it's slowly coming to a slowdown, expanding very slowly, so you can use the Liouville approximation again. You find that the field at late times looks like this, where bk is equal to alpha ak plus beta k, a adjoint of minus k, and bk is the annihilation operator for the vacuum state at late, or for the state rather, at late times, using the Heisenberg picture. In other words, you haven't changed your state. At the early times, I've taken the vacuum state annihilated by AK, the annihilation operator, and at late times it evolved into this BK. And there's no question about that. That's just a straightforward thing. Okay, and okay, and this transformation turns out to correspond to the creation of particle-antiparticle pairs of total momentum 0 from the vacuum, as required, of course, by conservation of momentum. And this is an example of a Bogoliubov transformation, as I explained in my physical review paper in 1969 in some detail. and in connection with particle creation by the expanding universe. Later, analogous Bogoliubov transformation involving sets of creation and annihilation operators were used by Steve Fulling, who is here, in his thesis at Princeton, and he used it to describe the so-called Rindler space-time of accelerating, a system of accelerating observers, and that was sort of Hawking cites Steve's paper in his original paper on black hole particle production, as he should. I mean, you know, as his, that was sort of where the connection came between the expanding universe and the black hole. Of course, what Stephen did was much more difficult and involved, and okay. Okay, and so if one more thing I should mention is that the connection between spin and statistics. As though it seems very simple what we're doing here, it turns out that already this gives you a way of getting the connection between spin and statistics, which is completely different from what Pauli did, because and actually very simple in this context. If you go through this same kind of expansion of fermions, which I also did in my thesis, you find that the conserved, what you would call the conserved Wronskian, for fermions, instead of giving you absolute alpha squared minus absolute beta squared equals 1, in order to have, it gives you a much more complicated looking equation, but involves a matrix which absolute, well, basically you take the square of a matrix, absolute value, and you subtract the second part. Instead of alpha squared minus beta squared equals 1, you get something like alpha squared being a matrix, plus absolute beta squared equals 1. It turns out that that's what you need in order to get the anti-commutation relations to be propagated consistently in this expanding universe. And later, that was used to limit spin statistics. It gives you the usual spin statistics relation. Okay. And I mentioned Fulling extending this thing to various orders. Okay, so now one last thing I want to say is that another thing we considered was that if you have a statistical density matrix describing your system in the initial state, the mixed state, then and if you have particles present initially, an average number of particles, then at late times the and this is significant with regard to inflation, in fact, which I'll point out a little later. If you have at late times this nk, and it's just given by the trace of the statistical density matrix times B adjoint B, where B is the late time annihilation operator and creation operator, and what you have in that case, instead of simply having beta squared as your expectation value of the number of particles in mode K, you also have a stimulated emission, stimulated creation from the vacuum occurring. And the result, which is again in my 1969 physical review paper and in my thesis, is that average number at late times equals average number at early times plus, so here we're taking that average number not to be zero. So when we look at our initial Minkowski space and we then start expanding, we've already got particles. This nk early is the average number of particles in the early Minkowski space. And then we have the usual beta k squared giving us the number of created particles if there were no vacuum, no particles already present rather. And in addition to that, you have this term 2 times the average number of early time particles present, assuming you started from not from a vacuum state. So you've got stimulated boson creation, and for fermions, as I showed, you have the opposite. You have not stimulated but suppressed particle creation. You know, in abeyance with the Pauli principle, but coming out of the field theory. Okay, so what we find, and this is will be significant when I talk about inflation in a minute, the average number of these spin zero bosons present at late times is increased by stimulated creation resulting from the presence of a non-zero average number of these particles at early times, and the opposite is true for fermions, as I said. Okay, so when we discuss the exponential expansion, what it seems to say is that if there were particles present initially, then you could greatly change the average number, increase the average number of particles that get created or that are present at late times. So, okay, and then I just mentioned some work that relates to that I did with Ivan Araujo and Jose Navarro-Salas more recently. Okay, now let me just get to the end of this if I can. So as I mentioned, okay, let's talk about exponential expansion. Let's start with a quantized minimally coupled scalar field in an initial flat space-time invariant under the 10-dimensional Poincare group, and suppose, which determines the vacuum, of course, the 10 symmetries, and suppose that the quantized scalar field is in its vacuum state having those symmetries. Let us assume that our universe undergoes a spontaneous fluctuation of some sort with A of t, A dot, and A double dot at least continuous, and that it eventually takes it to an exponentially expanding spatially flat universe with A of t proportional to e to the ht with h constant. So, so after a time, suppose the quantized field in this exponentially expanding de Sitter universe has settled into a state having the 10 de Sitter symmetries. So it'll go through some kind of fluctuations or something, and then settle down from the Poincare symmetries to the de Sitter symmetries, which, as we know, that's the Bunch-Davies vacuum symmetries. And okay, and most of this is stuff I need not go into details here. Okay, and let's say that this is basically inflationary type of universe we're talking about, and there's something, let's say, that brings it to the kind of universe we have, some reheating or, you know, the usual kind of thing that's discussed. And then what you can find just from the symmetry, the fact that it's, let's talk about the de Sitter stage for a moment. So remember that at late times the annihilation operator is a linear combination of the creation and annihilation operators in the early time space with an alpha and beta k of T1 now, where T1 is a time when the Sitter symmetry holds, and this corresponds to production of pairs. And we also have, as a consequence of the field equations, that alpha squared minus beta squared is 1, and so you have the correct commutation relations. After de Sitter invariance has been reached, we expect the number of particles present per unit physical volume is constant, of course, to maintain the de Sitter invariance for T greater than T1. Hence, and this is what I explained in my discussion with Hoyle, hence, if T is greater than T1, it follows that beta k squared divided by A of T cubed is a constant. And because your density of particles present physical density is a constant to maintain the de Sitter, because we're maintaining de Sitter invariance. And so during a period for which inflationary equilibrium has been reached, we must have absolute value of beta squared divided by at time T2 divided by A of T at time T2 cubed is equal to the same quantity at time T1, where both of those times are during the de Sitter stage. And since A of T, we're in de Sitter, and A of T in the spatially flat situation goes as e to the ht, that implies, because of this A of T in the denominator here, that beta squared is proportional to e to the ht cubed after inflationary equilibrium has been reached. So we know from that how many particles, the average number of particles that have been that are present during the inflationary stage is proportional to this. Okay.
Is this more or less the same thing as your earlier equation where the particles created were through stimulated emission of the earlier?
No, the stimulated emission will.
So
Yeah.
that leads to exponential growth.
Yes. Yes.
Is this sort of the same thing?
This gives you the beta squared, but the point is, if you already have particles present before it started, you're getting a stimulated. We'll see in a minute. I was just coming to that.
Well, that leads to exponential growth, right? If you have particles present stimulating more particles, then they are now present, so they'll stimulate more.
Yeah, and you get a lot of
which is
growth.
exponential growth. So is that where this came from, more or less? Oh, okay, go ahead. Yeah.
I'll show you. I mean, I wrote the equation. We're almost at the end here. So this is even if you have no particles present.
Yeah, but once you've got some, they stimulate more.
Yeah, you have that formula here, which followed from the statistical density matrix. And what it shows you is that you have this 2nk, twice the average number of bosons present at early times, and that comes in, that turns out to be the dominant term.
Right, so that's exponential.
Yes, that's exponential. Yes. nk early is a constant, though.
Well, but then the end.
Then the beta squared.
This becomes the new early, and so on. So
Yes. Right. So anyway, so that turns out that when you look at what it has to be, it's even without the particles present initially, you find it's a very large production rate that you'd have to have in the present universe if you wanted the steady state.
So
Yeah.
there's no inflaton or anything, it just happens by itself?
Yes. Oh, okay. I can't see, Laura. Just tell me, okay?
2 minutes.
2 minutes. Okay. Right. All right. So that's good enough for this. Let me just go on to mention one other thing. So I also looked at the, let me find, oops, here we go. Okay. So Klaus Kiefer mentioned this paper. So when I was looking at the particles in the early universe, I calculated the probability distribution for those particles, created in each mode. And there was some question around this time, 1975, that whether you had whether you really had a black body distribution of created particles by the black hole. We knew from Hawking's famous calculation that indeed you have the average number being, you had the Planck distribution, but for the distribution of modes, there was some question, and that was raised by Bob Wald. And so when I was looking at the expanding universe in my thesis, as I said, I calculated the probability distribution by a certain method. And it turned out that I followed that method, of course, with Hawking's famous results and his wonderful calculation of the black hole radiation in detail. And it turned out it gave you a very simple way of proving the, all right, here we go. All right, so here, this is Hawking's famous results I first go over in the paper. And by the way, Stephen also proved this in a more elegant way than what I'm doing here, and also Wald. So it turns out that you can use the same method I had used in my thesis to look at the probability distribution of the created particles in the expanding universe to calculate the probability distribution in this in this situation of the black hole. And because I only have 2 minutes left,
That was 2 minutes ago.
I will just jump to the answer. As you might guess, you end up here when you do it carefully, by the same kind of thing, using commutation relations with creation and annihilation operators. You find that you have the black hole probability distribution if you neglect the backscattering from the geometry of the space-time, if it's not, since it's not exactly flat, which is taken into account in the calculations of Wald and also Hawking. Here I did it for the case ignoring the backscattering and then putting in the factor in front for to make it thermal instead of pure black body, as I mentioned in the paper. Okay, so
Thank you.
thank you.
So,